ठीक है ना. So angular velocity is rate of change of angular displacement. That means omega can be written as d theta by dt. Omega can be written as d theta by dt or delta theta upon delta t, depending on your situation. ठीक है, you know it is similar to linear. ठीक है, if someone asks you the instantaneous angular velocity, you will use d theta by dt. If someone asks you what is the average angular velocity, average angular speed, then you will use this formula. This is for instantaneous. Instantaneous, this is for average. Okay, so this is how you define angular velocity. Simple, you know this. Okay. Acha. Now I am saying it angular velocity. That means it must be having some particular direction also. Okay, this is about magnitude and all. Okay, but you also need to know what should be the direction. Okay. Now to represent the direction of angular velocity, okay, there are two methods. Okay, two ways in which we can represent angular velocity. One is using clockwise and anti-clockwise direction. Okay, that is the you can say the flow of the motion. Okay, that is one method, and the other method is by a vector. Okay, so we will discuss both of them. Now see, angular velocity can be in two types. Suppose I have an object. Okay, this object is rotating like this. Okay, it is going like this. So you can see that this object on a circular path is going in anti-clockwise direction. Okay, it is going in anti-clockwise direction. So we can denote omega just like this. Okay, just draw an arrow, just draw a curve in anti-clockwise direction. Okay, arrow in anti-clockwise direction, and write omega above it. That will be representing angular velocity. Okay. Another method is other direction. Sorry, not another method. The other direction is if the particle goes like this in clockwise direction. Okay, so if it is going in clockwise direction, so again omega can be just written by a arrow in clockwise direction like this. Okay, so this way the direction of angular velocity can be represented. You can say it can be shown. Okay. Other method is your vector method. Okay, you can draw a vector representing the direction of angular velocity. And how to calculate that vector? It is very simple. Okay, it is just your right hand thumb rule. You must have done this right hand thumb rule. You must have done this in many of the chapters. Okay, magnetism you must have done, in torque you must have done, in all that you must have done. So same thing we are going to do here. Okay, what you do is you curl your right hand finger. Okay, first four fingers which you have in your right hand, you curl it in the direction of the motion. Okay, like in case of anti-clockwise, in case of anti-clockwise motion, when the particle is going like this, try to wrap your hands around this motion in anti-clockwise manner. Okay, try to uh, capture this complete motion using your right hand fingers in anti-clockwise manner. If you curve your fingers in anti-clockwise direction, your thumb, you can see your thumb will be pointing upwards. Okay, away from the paper. Okay, away from your plane of paper. Okay, so in this case the omega can be drawn like this: dot omega. You know dot and cross representation, I guess. And dot means coming out of the plane, cross means going into the plane. So here, since the thumb is coming out, I can represent it like this. Okay, it can also be represented at the center also. Dot omega like this. Okay, that means there is a vector. Okay, there is an angular velocity vector coming out of the plane. Okay. Similarly, for the clockwise motion, okay, similarly for clockwise motion, if a particle is there, and it is going in clockwise direction. Okay. Now, if you try to curl your fingers in the direction of clockwise motion, okay, if you try to wrap your hands around this in clockwise direction, your thumb will be in this case coming into the plane. Okay, it would be going towards the paper. Okay, that means the direction of omega will be across like this. Okay, it can be represented either at the center or just besides motion. Okay, anywhere you can represent it, it is a vector. Okay, it would be understandable wherever you write it. Okay, so these are the two ways of representation of a angular velocity. Okay. Acha. Any doubt in this, anybody? Basic thing, simple thing. Okay, I guess it is known to everybody also. Okay, just for a recap, I was doing this. Okay. Now, acha, SI unit was left. No doubt, that's it. Okay. So SI unit. Okay, if you calculate the SI unit of a angular velocity, okay, it comes out to be radians per second. Simple. Delta theta upon delta t. Delta theta dimension is radians. Delta theta unit is radians, and delta t units is seconds. So radians per second is the SI unit of this angular velocity. Okay. If you want the dimension of omega, okay, dimension of omega can be written as radians. Radians is a dimensionless quantity m0, l0, t0 divided by seconds. Seconds dimension is t raised to power 1. So basically you can see here that the dimension of omega is coming out to be 1 upon t or t minus 1, whatever, whichever is suitable. Okay, most of the time it is written as t minus 1, so that is only preferable. So dimensions of omega is t minus 1. That means if you see here, according to the dimension, okay, according to the dimensions of angular velocity and frequency, okay, angular velocity and frequency are same. Okay, so that is why when you were doing your SHM, you must have seen that in SHM, in simple harmonic motion, the omega is not called as angular velocity. It is called as angular frequency. Okay. Depending on the situation, your omega can vary, okay, because its dimension is similar to frequency. At some places where it is circular motion, it will behave like velocity. At some places like SHM, it will behave like frequency. Okay. So you can just write a note over here that since, not since, let's write it that omega of dimension of omega is t minus 1. Also dimension of frequency f. Okay, this is also t minus 1. So therefore, omega and f can be replaced, can be interchanged, you can say, not replaced, can be interchanged as and when required. Interchanged. Okay. So depending on the situation, depending on the motion of the particle, okay, if it is circular motion, I will say it angular velocity. If it is a SHM, I will say it as angular frequency. Okay, because its dimension is similar. Second, t minus 1. Okay, hope it is clear. Simple things. Okay, you must have observed this also. Okay, while you were studying in 11, must have just seen this. Okay, so these are basic things, you must have observed it. Okay. Acha. This was angular velocity. Acha. Now let's move on to angular acceleration. Angular acceleration. Okay. So what is angular acceleration? Again, it is denoted by alpha. Okay. Angular acceleration is nothing. It is basically the rate of change of angular velocity. Same rate of change of angular velocity. Okay, same as linear. Okay, everything is similar to linear. Just there is a replacement of terms. Okay, in linear motion there was displacement. Here it is angular displacement. In linear it was a velocity. Here it is angular velocity. There it is acceleration, here it is angular acceleration. Everything is same, just a word of angular is being constantly added to the terms. Okay, meaning is also the same. In fact, the formulas, if you see, they are also similar. Okay, they are also similar. So what we can write here is alpha is equal to d omega by dt, delta omega by delta t. Okay, these are the formula. Again, the same logic. D omega by dt will be used when you have to calculate instantaneous. Okay, for calculating instantaneous acceleration, instantaneous angular acceleration, I will use d omega by dt. If I have to calculate average acceleration, I will use delta omega by delta t. Simple. Okay, these are all basic things. Okay, we have done this many a times. Acha. Now, SI unit. Okay, SI unit of angular acceleration will be, okay, you can guess it. It is radians per second square. Simple. Okay, delta omega by delta t. SI unit of omega is radians per second. Time, you are dividing it by time, so you are dividing it by seconds. So it becomes radians per second square. Acha. The dimension, again, if I are talking about the dimensions, so you can see that radian, okay, the dimension of radian is dimensionless, it is 1. So that will become 1 upon second square time square. So this can be written as t minus 2. Okay, these are the basic things which you have to keep in mind. Okay, if you are able to keep these things in mind, basics will be clear. Okay, your basic sense will be strong. Achha. Now I am talking about acceleration. Okay, acceleration cannot be a scalar quantity. It okay, am I audible? Yes. ठीक must be some network problem. ठीक है ठीक ठीक अच्छा. So where was I? Angular acceleration. Now see that direction. See, acceleration is a vector quantity, so definitely we need to calculate the direction also. Okay, we have the uh, magnitude. We need to calculate the direction also. Now, how to calculate the direction? That is a different matter. Okay, calculation of direction of acceleration is a bit difficult. Okay, not difficult means it is not for the this chapter. Okay, why I am saying, because if you remember linear motion, okay, the source of generation of acceleration is force. Okay, whatever direction the force is, net force is there, in that direction only linear acceleration is there. Sorry, sir. In whichever direction the force will be there, in that direction only linear acceleration will be there. So in this also the similar thing happens. Okay, you know that the angular analogy of force is torque. Okay, so in whichever direction torque will be there, angular acceleration will be in that direction only. Okay, the direction of acceleration, you must remember, is independent of the direction of angular velocity or velocity in that case. Okay, it can be in any direction. Like, just for example, see, suppose I have a particle. Okay, its angular velocity is like this. Okay, in anti-clockwise direction, but it can have acceleration like this also, angular acceleration in clockwise anti-clockwise direction also, and in clockwise direction also. Both are correct. Okay, it depends on the situation. If it is slowing down, okay, if it sorry let's see first. If it is speeding up, suppose its angular velocity is increasing, okay, if omega is increasing, then the alpha and omega will be in the same direction. Okay, if omega is increasing, simple logic. If your velocity is increasing, your acceleration and velocity are in the same direction, same logic. Okay, same logic as linear. And if your angular velocity is decreasing, if your angular velocity is decreasing, alpha and omega are in opposite directions. Alpha and omega are in opposite directions. Okay, same as linear, same as linear. Yes, it is like angular retardation. Very good. Okay. The second case is basically angular retardation. Okay. So it is similar to linear only, just in angular terms. That's it. Okay. Direction is very similar to linear. Okay. Just in case of angular, it is happening. Whatever happens in linear, same thing happens in angular also. Okay. The second, you can say the second variation is that if your omega is like this, okay, omega is like this, if your particle is going clockwise, so again your alpha can be in two directions, like this and like this. Okay, again the same logic, omega and alpha are in same direction, so your omega will be increasing. Okay, it will be accelerating, and omega and alpha are in opposite direction, so omega will be reducing, it will be retarding. Okay, so that is same as your linear acceleration. Okay, whatever direction is there, it can happen. Okay, the motion will be as such. That is a different thing. Okay. And so I guess these things are understandable to you. Okay, these are just the basics. Any doubts, anybody? Simple things, basic things. Okay, you must be knowing this. ठीक है, no doubts. Good. ठीक है, अच्छा. Good, good. अच्छा. Now, nice. ठीक. Now, this was angular acceleration. ठीक है, we have done angular acceleration and everything. अच्छा. Now, let's talk about similarities between. ठीक है, similarities, or you can say just the similarity between linear motion and angular motion. ठीक है, they are vivid. ठीक है, they are very very similar. ठीक है, just the values are changing, formulas are almost equal. ठीक है, almost same. ठीक है, so let's see linear motion and angular motion side by side. ठीक है, we will see the similarities, or you can say the differences between linear and angular. ठीक है, not the differences, similarities only. ठीक है, now see, in linear motion you have linear displacement s. ठीक है, not so let it be s only, linear displacement. ठीक है, for linear displacement we have angular displacement. ठीक है, you can in fact say that if I want to replace something in linear from angular, I will replace s with theta. ठीक है, I will replace s, r, x or whatever with theta. ठीक है, similarly in linear where I have velocity, in angular I have angular velocity. ठीक है, similarly in linear where I have acceleration, here I have angular acceleration. ठीक है, now even in fact the definition, ठीक है, if you see the definition of these terms, like velocity in linear, if you see the definition of velocity, it is ds by dt. It is ds by dt or delta s by delta t. है ना? So here also omega is defined as what? It is defined as d theta by dt. See what we have done. We have just replaced s over here with theta and v over here with omega. Okay. So there are very good similarities. You can say very vivid similarities between linear and angular motions. Okay. Again, acceleration. If I'm talking about, okay, acceleration can be written as yes. Mute. Somebody's mic is unmuted. Just mute your mics. Okay. So where was I? Acceleration. Now in linear, acceleration can be written as dv by dt. ठीक है, or there is another formula for it, that is v dv by ds. ठीक है, you must have done this. Whenever velocity is represented in the form of displacement, ठीक है, instead of time, whenever the velocity is a function of displacement instead of time, to calculate acceleration we use the second form. ठीक है, second form of acceleration. So here also in angular also, alpha can be written as, ठीक है, first is dv by dt, so just replace v with omega, that's it. So it will become d omega by dt. That is the basic definition, है ना. Second, the second form of alpha, ठीक है, it can be written as v can be replaced as omega, so omega d omega by d theta. ठीक है, it will be omega d omega by d theta. ठीक है, so there are very vivid similarities. ठीक है, you can clearly see the similarities between linear and angular motions. ठीक है, अच्छा, now these are the similarities. ठीक है, these are the similarities, but still you cannot say that linear displacement is equal to angular displacement. ठीक है, for our convenience we can replace it in formulas. ठीक है, we can replace it anywhere else. ठीक है, like just let's see. You must have studied equation of motion. So there is one and only criteria to define equation of motion, that your acceleration should be constant. ठीक है, whenever your acceleration is constant, you can apply equations of motion, as simple as that. ठीक है, अच्छा. Now what are the equations of motion? We can see, you remember those है ना, three equations of motion. V is equals to u plus at, s is equals to ut plus half at square, and v square is equals to u square plus 2as. ठीक है, these are the three equations of motion in linear motion. ठीक है, linear motion, straight line motion, है ना. Similarly, ठीक है, the similarity does not end just on the basics. ठीक है, you can similarly write equations of motion for angular motion also. ठीक है, equations of angular motions you can say. ठीक है, equations of angular motion. So again, equations of angular motions will be applicable when your alpha is constant. ठीक है, I replaced acceleration with alpha, angular acceleration, that's it. Alpha is constant, equations of angular motion is possible, you can use it. ठीक है, it is valid. ठीक है, now how to replace it? ठीक है, v is equals to u plus at. V is what? V is the final linear velocity, so here it will become final angular velocity, omega final. ठीक है, u is what? U is initial linear velocity, here I will replace it with initial angular velocity. ठीक है, plus acceleration can be replaced by alpha t, that's it. ठीक है, this is the first equation of angular motion, same as linear motion. Again, s is displacement can be replaced as angular displacement, theta. Second one is equal to u can be replaced as omega initial, time will remain the same, time does not change in linear or angular, it remains the same, and I don't change it into something else. Okay, it will remain the same. Acha, so theta will be equal to omega initial t plus half acceleration is alpha t square. Khatam. This is the second equation of angular motion. Third, v square is equals to u square plus 2s can be written as omega final square, omega initial square plus 2 alpha theta. These are the three equations of angular motion. Simple. Okay, you don't even have to do derivations about it, because see, nobody is going to ask you derivation in NEET, and nobody is going to say what is the derivation, how did you get these things. Okay, you just need to have tricks for yourself so that you don't have to remember much of the things, but you can solve much of the questions. Okay, so just those small tricks are these, that just replace values from linear into angular. Okay, So these are the similarities, you can say. These are the connections which you can make between linear and angular. है ना? अच्छा, but I can never say that my linear displacement, yes, है ना? I can never say that my linear displacement is equal to angular displacement. ठीक है? There must be some relation. There must be some relation between linear displacement and angular displacement. ठीक है? You cannot just say that s is equal to theta. This is wrong. ठीक है? There must be some connection. There must be some equation, some formula which is connecting these two terms. ठीक है? Otherwise, how can there be so much similarity? ठीक है? If there are so many similarities, if it is so much common, then there must be some link connecting them. ठीक है? Common link. ठीक है? It should be a very common link which you already know. ठीक है? It is not something new also. You must have studied this in fact 5th 6th. ठीक है? That is the arc length. ठीक है? Formula of arc length. What is the formula of arc length? ठीक है? Don't write this as s equal to theta. That will confuse you only. Yeah. Formula for arc length, if you remember, if s is the arc length, r is the radius, and theta is the angle made by the arc, then using the formula of arc length, ठीक है, using the perimeter formula, yes, ठीक है, you can write s is equal to r theta. This is the connecting chain, ठीक है, this is the connecting link between linear motion and angular motion. ठीक है, you can see here that you have linear displacement connected with angular displacement by a term of radius. ठीक है, in whichever manner it is used, but it is connected. So this is the common, you can say, common link. ठीक है, it is used very, means it is like कहीं भी use हो जाता है. ठीक है, you cannot predict where it will be used, but it is very commonly used. ठीक है, these are basic definition, basic links between the motions. ठीक है, now this was for displacement. What about velocity? Just differentiate it. Okay, if you differentiate the equation with respect to time, okay, if you differentiate this equation with respect to time, LHS will become what? ds by dt, that is velocity. R is constant, radius of the circular motion remains constant, so R is constant, so R will be out of differentiation. What will be differentiated? Theta. D theta by dt will be there. D theta by dt is omega. So V is equals to R omega. Another formula, you must have done this. Okay, there is a very long derivation behind it. In fact, V is equals to R omega is having a long derivation. Okay, no need. Who is asking the derivation? Nobody. Okay, again, differentiate it one more time. Okay, differentiate it one more time with respect to time. Okay, so again, left hand side will become acceleration. Okay, and right hand side will become R is constant. This will come out to be alpha. A is equals to R alpha. Okay. Achha, one thing you have to remember here is that this acceleration which we are writing, okay, this acceleration, linear acceleration which we are getting is your tangential acceleration. Tangential acceleration. Okay, this is a very important thing. You will get confused, sir. What is the formula for centripetal acceleration and tangential acceleration? So this acceleration, whichever acceleration which we have used here, okay, is your tangential acceleration. Okay, for circular motion. Okay, in circular motion, you know that particle will have two kinds of acceleration, tangential and centripetal. So tangential acceleration is what we are talking about here. Okay, because that is the term which can be used in linear motion. Okay, centripetal is the thing which creates circular motion. So that cannot be used in linear. Na? Okay, you can remember it like this. Or if you're not getting the idea behind it, let it be. Just remember that this is A tangential. Okay, A tangential is equals to R alpha. That's it. Okay, so these are the links. Okay, these are the links which connect your linear motion with angular motion. Okay. Acha. Any doubts, anybody? ठीक है, because this is basic thing. ठीक है, you want to write, you want to take the screenshot or anything, you can take it. ठीक है. Any doubts, anybody? Because these are the basic things. If you are confused over here, then it won't help anywhere. Anybody? ठीक है, if anybody has any kind of doubt, don't worry. ठीक है. ठीक है. ठीक, good. So everybody is getting this, है ना? अच्छा. हाँ. ठीक है. So let's move forward. And so these were the basic links, or you can say the connections or the basics of circular motion, which you have to remember completely. Okay? Everywhere, anywhere it can be used. Okay? You must have seen it in electrostats also. It is used. Magnetism also it is used. SHM also it is used. Everywhere it will be used. Okay? So circular motion is a very common motion. Okay? So it is used anywhere. Acha. Next is where were we? This was the third or fourth. Third. Okay. So the next term is your centripetal acceleration. Centripetal acceleration. AC. Okay. Centripetal acceleration, if we are talking about centripetal acceleration, so the basic of centripetal acceleration, you know. Okay, the basic is that it is a force, it is a acceleration, okay, which is always directed. Acceleration always directed. Directed towards the center of motion. Towards the center of motion, circular motion. Okay, we are talking about circular motion only, so it is not necessary to mention here. Okay, so you can just write center of the motion. Okay, so this is called a centripetal acceleration, and acceleration which is always directed towards the center of the circular motion. Okay, so like suppose if we have a circular motion like this, a particle is going in path like this, it is at over here, at some instant it is over here, at another it is over here, here and here. So in all these four locations, it will have some kind of centripetal acceleration, which is directed towards the center. Suppose it is at A point. So at A point, the centripetal acceleration is towards the center O, that is towards the left. If it is at B point, the centripetal acceleration is towards O, in this case, that is downwards. If it is a C point, it is towards the right. If it is at D point, it is upwards like this. Okay. So irrespective of the location of the particle, okay, irrespective of the location of the particle, the centripetal acceleration will always be towards the center. That is why it is called a centripetal, towards the center. Centripetal means. Okay. So this is the centripetal acceleration. Centripetal acceleration formula is v square by r, okay, which is important for us. Okay. The particle must be having some velocity at A point. Okay. The radius of the circular path is fixed. So the centripetal acceleration will have a value of v square by r. Okay, at A point. If its velocity changes and at B point it is something else, suppose it is VB, here it was VA, then centripetal acceleration at A can be written as VA square by R. Okay. If the centripetal acceleration at B, if the velocity at B changes to VB, okay, suppose it is changing, it is varying, it is possible. Okay. So if it is varying, the centripetal acceleration at point B can be written as VB square by R. Okay, so depending on the position, depending on the speed at that point, the value of centripetal accelerations formula will be v square by r. Okay, or we have just seen that v is equals to omega r is true. Okay, you can replace v as omega r. So if you replace it omega r, so it comes out to be omega square r. Okay, so this is the formula for centripetal acceleration which you have to remember. Derivation is not important to us. Nobody asked derivations, and you don't need it also. The formula and its application is important for you. Okay, so this is centripetal acceleration. Okay, it is acceleration. So unit. Okay, if we are talking about SI unit over here, then it is again meters per second square only. Okay, it is a linear acceleration. Centripetal acceleration is a linear acceleration. It is not angular acceleration. Okay, the SI, the dimensions of this will be LT minus 2. Simple, same as that of normal linear acceleration. Acha. So this was centripetal acceleration. Next is tangential acceleration. Okay, fifth is tangential. Tangential acceleration, A tangential. Okay, it is denoted by AT small t, or whichever symbol you want to use, you can use. Okay. Acha, A tangential. What is A tangential? Acceleration along the tangent of the circular path, circular motion. Okay, the acceleration which is along the tangent of the circular motion is called as tangential acceleration. Okay, this is not a very regularly used term. Okay, tangential acceleration will be used sometimes. Okay, not always, but still, if it comes, you should know. So suppose the particle is over here and it has an acceleration, linear acceleration in this direction. Okay, instead you can see here now that centripetal acceleration is towards the center, but acceleration which is along the tangent, this is the tangent at this point, this acceleration is in the direction of the tangent. So means parallel to tangent, not the direction, it is parallel to tangent. It can be in upward direction also, it can be in downward direction also, depending on the question, depending on the situation. Okay, so this acceleration is your tangential acceleration which is along the tangent. Okay. Achha, now what is the formula for this? We have already seen one formula, that is alpha r. Okay, its formula is alpha r, or dv by dt, or v dv by dt. Okay, I have already told you. Okay, these formulas in the similarities. Okay, similarity portion. Achha. So these are the basic formulas of tangential acceleration. Achha. Now, a curiosity will arise within you that, sir, why are there two kinds of acceleration, linear acceleration in circular motion? Okay, why are there two kinds of linear acceleration in circular motion? Now, these two accelerations will create a type of different types of circular motion. So you can just write a note that what are the what is the work of centripetal acceleration and what is the work of tangential acceleration. Okay, so let's first write a note about centripetal acceleration. Okay, a centripetal, what is the work of this acceleration? So you will see here that when I drew tangential centripetal acceleration, I was not at all interested what is the direction of motion of the circular particle, of the particle. Okay, it can be clockwise, it can be anti-clockwise, it can be anything. Okay, its velocity may be increasing, its velocity may be decreasing, but the centripetal acceleration will always be there. That means a unique characteristic of circular motion is that there is a centripetal acceleration. Okay, so centripetal acceleration, you can say, is the source of circular motion. It creates circular motion. creates circular motion. ठीक है, why it creates circular motion? Because this is the acceleration which constantly changes, which constantly changes the direction of velocity. ठीक है, it does not change the magnitude. You can write it in bracket, does not change the magnitude. ठीक है, it does not change the magnitude of the velocity, but it changes the direction of velocity constantly. ठीक है, so that is why a circular motion is created. See, just for understanding, I am drawing this. ठीक है, you don't have to draw it. ठीक है, just for understanding, I am drawing it over here. That, see, suppose a particle is over here. ठीक है, I have given it a linear velocity like this. ठीक है, I have given it a linear velocity like this. Now what is happening is that because of this linear velocity, the particle should have moved like this. ठीक है, it should have traveled over here after 1 second, just for example. ठीक है, after some time it should be over here, but it is where? It is somewhere here. It is somewhere here on the circular path. Why? Because there must be an acceleration, there must be a force which is pulling it towards the center. Instead of going in this path, instead of going along the straight line, because of this centripetal acceleration, because of the centripetal force, if there is acceleration, there will be force. So because of that force, because of that acceleration, you can say the particle is bent in this direction, and instead of going in a straight line, it goes in a circular path like this. Okay, so what it has done is that when it is at this point now, okay, you can see that its velocity is like this. And so you can clearly see that its velocity should have been like this. Yes. Tangential and centripetal acceleration are both linear accelerations. You have to remember this. Okay, I guess I have not written SI unit over here. Okay, SI unit you can write it over here. SI unit is meters per second square for this also. Okay, dimension of tangential is LT minus 2 only. Okay, so both are linear accelerations, but their work is different. Okay, they have different works. Okay, that is why it is creating two linear accelerations are able to create a circular motion. Okay, because of the work they are doing, because of the work they do to make the motion circular. Okay, so here what I said was, see, its velocity was in upward direction. Okay. How it is linear? See, linear means something which can be represented along a straight line. That is linear. Okay. Now, when I drew acceleration, centripetal acceleration like this, is it not along the radius? And is not radius a straight line? Okay, so it is a linear acceleration. Okay. When it is at, suppose the different locations, suppose it is over here, its centripetal acceleration is like this, no doubt. Direction has changed, but it is still representing, it is still along a straight line. Okay, it is still along a straight line. Okay, it is always linear in motion. Okay, linear in nature. Okay, the line can be changing constantly. Now see, angular velocity. When I am talking about angular velocity, I draw it like this. Is this any straight line direction? Okay, so angular velocity is angular quantity. Okay, it is an angular, you can say, term. But linear velocity will be along a straight line. It will be having a straight direction. Okay, this is the difference. Okay, that is why centripetal and tangential. See, tangential if I draw, it will be like this. So that is along the straight line only. Okay, good. Now, nice that you are getting it. Okay, so these are just basics, no problem. Ask anything. Okay. So where were we? Centripetal acceleration. Okay, so see the centripetal acceleration, the direction of velocity of the centripetal acceleration should have been upwards, but it is not. It has been rotated in this direction. It has been changed in this direction. And which velocity, which acceleration is creating that? It is the centripetal acceleration. Okay, so this is the work of centripetal acceleration. You have to always remember centripetal acceleration is the acceleration which changes the direction of velocity but not its magnitude. Okay, it changes the direction of velocity but not its magnitude, which is what I have written in this point. Okay, so sorry, I had a call, so that is why I got disconnected. But okay. Am I audible to everybody? Yes. ठीक है. अच्छा. ठीक है. So we were at centripetal acceleration. ठीक है. We were at centripetal acceleration and we discussed what is centripetal acceleration. That what is the work of centripetal acceleration? ठीक है. That is it constantly changes the direction of velocity and not its magnitude. ठीक है. It changes the direction of its uh, velocity but not its magnitude. This is the work of centripetal acceleration. Hence, we can say that wherever there is a centripetal acceleration, there must be a circular motion associated. Okay. If there is a circular motion, there will be a centripetal acceleration. And if there is a centripetal acceleration, you can say there will be a circular motion. Okay. I'm not going to write this because this is not a statement. Okay. This is not a fact. Okay. Because circular motion, if centripetal acceleration is there, it could be a parabolic motion also. But okay, for our convenience, we can say that it is circular only. Okay, because parabolic motion is not there in our syllabus. ठीक है, in detail. ठीक है, that projectile is a different thing. ठीक है, projectile is also parabolic path, but that is a different matter. That is projectile. ठीक है, so that is a different thing. I am not going to write a statement about it, but yes, you can definitely say that whenever there is a centripetal acceleration in the motion, okay, whenever there is a centripetal acceleration in the motion, there must be a curvature of path. Okay, the path must be having some kind of curvature, whether it be parabolic or circular doesn't matter. Okay, if the motion is like this, suppose it is like this, so you can say that constantly there is some kind of centripetal acceleration. Just you can break this down like this. Okay, see this first part which is there, its centripetal acceleration will be somewhere like this. Okay, the center will be towards the upwards. Okay, center will be towards upwards like this something. Okay, for the second part, your centripetal acceleration will be like this, constantly towards a center in the down, in the bottom. Okay, again for the third part it will be upward, again for the fourth part it will be down, and so on. Okay, so whenever there is a curvature, okay, whenever there is a turning in your path, okay, there will be some centripetal acceleration associated with it. Okay, because the work of centripetal acceleration is this only, to change the direction of velocity. So wherever there is a change in direction of velocity, whenever there is a change in direction of velocity, you will see a centripetal acceleration being formed. Okay, even in projectile. Okay, these are just examples, you don't have to draw. Okay, this is just for understanding. Okay, this is your projectile motion. Okay, now you can see here that its velocity was like this, initial velocity was like this, then its velocity became like this, then its velocity became like this, and so on. So you can see here that the direction of velocity is changing. So if the direction of velocity is changing, it will have centripetal acceleration over here, the centripetal acceleration over here, some centripetal acceleration over here, and some centripetal acceleration over here. Okay, they will not be pointing towards the same point. Okay, they will not be pointing towards same point because it is not circular, it is parabolic. Okay, it will be along a axis. Okay, this point will be over here, this will have center over here, this will have center over here, this will have center over here. That is a different matter. But since the direction of velocity is changing, the centripetal acceleration will be there. Okay, we don't discuss it, doesn't matter, it is not there. Okay, it doesn't mean that it is not there. It is there, but we are not discussing it. Okay, because it is not useful to us. What we will do by calculating the centripetal acceleration in projectile? Okay, it is not useful. Okay, so this is the, you can say, the work of centripetal acceleration, to change the direction of velocity. Achha, so forget all this. Okay, this is just for explanation. If you get it, well and good. If you are not getting it, don't worry. Okay, you don't have to understand those things. What you have to remember is, what you have to understand is that centripetal acceleration changes direction. Okay, centripetal acceleration changes direction. Acha. Now let's talk about tangential acceleration. Tangential. Okay, so what is the work of tangential acceleration? It is just the opposite of centripetal acceleration. Okay, just the opposite. The tangential acceleration changes the magnitude of velocity. Magnitude of velocity, and not the direction. Direction of velocity. Okay, so these two forces, you can say, are working together to create a circular motion. Okay, means that one is changing the direction of the velocity and the other is changing the magnitude of the velocity. When direction and magnitude change simultaneously, they create circular motion. Okay, you can see it like this. So this is the work of tangential acceleration. Suppose I have drawn so a particle is going in a circular path like this. Okay, it is going in anti-clockwise direction like this. ठीक है. Now suppose it has a tangential acceleration in this direction at this point. ठीक है. So when it moves, ठीक है, when it moves in a circular path, there will be centripetal acceleration to create, there will be a centripetal acceleration to create the change in direction. We are not discussing about that now. ठीक है, we are discussing about the tangential acceleration. That because of tangential acceleration, as it will reach point B, ठीक है, it starts from point A, it had velocity va. When it reached point B, its velocity at point B was greater than velocity at point A. Magnitude, ठीक है, speed you can say, ठीक है, magnitude at point B was greater than the magnitude at point A. ठीक है, direction changed because of centripetal acceleration, that we will discuss in another part. ठीक है, but here since we are talking about tangential acceleration creates change in magnitude. ठीक है, so here also a tangential acceleration will be there. ठीक है, in most of the cases it will be there. So again when it moves to point C, suppose, ठीक है, it moves to point C, it will have a different velocity which will be greater than the previous velocity. ठीक है, direction changes because of tangential, centripetal, but magnitude changes because of tangential. ठीक है, another type you can say, another variation in tangential acceleration is, suppose the particle is at A point, its velocity is va like this, but the direction of tangential acceleration is in the opposite direction. ठीक है, I told you acceleration's direction is never determined by the direction of velocity. It is always determined by force. Yes.
What is velocity is constant? Is the magnitude necessary to change?
नहीं, हाँ नहीं, see, velocity is constant. You cannot say velocity to be constant in circular motion. That is
okay,
not possible.
Speed. Okay, I consider that as speed then.
Yes.
If speed is constant, then tangential acceleration shouldn't, magnitude shouldn't change, right?
Yes, it will become zero. If your velocity, if your speed becomes constant, if your magnitude of velocity is constant, then the tangential acceleration will become zero. That was my third case. Okay, these are the three cases of. Okay, that I will tell you. Don't worry.
Okay, thank you. Okay.
Yeah, no problem. Okay, so now see, suppose at A point the velocity is in upward direction. Okay, there is some value magnitude of velocity, and tangential acceleration is in the backward direction. So when it reaches point B, okay, after some time it will reach point B, it will have some velocity vb. Okay, direction changes because of centripetal acceleration. We are not worrying about that, but the magnitude would have changed and decreased in this case. Okay, it would have decreased in this case. So velocity at B, speed at B, magnitude of velocity at B will be less than magnitude of velocity at A. Okay, why? Because the tangential acceleration was in the opposite direction. Okay. Similarly, as it will reach C, okay, as it will reach C, velocity at C point will again be reduced. Okay, it will be less than the previous one. Okay, and so on. It will keep on reducing. Okay, till what point it will reduce, we don't have to worry about that. Okay, we just are talking about the effect of tangential acceleration. Okay, now this was the basic two cases. Okay, another case is there which I just discussed with him. Okay, that if I have no tangential acceleration, simple. Okay, if a particle is here at A point, it has some velocity va, but A tangential is zero. It is possible A tangential can be zero, but always remember A centripetal cannot be zero. Okay, if you want, you can write here that A centripetal for a circular motion can never be zero. If A centripetal is zero, it is not a circular motion. Okay, if it is a circular motion, A centripetal cannot be zero because constant direction changing is occurring. ठीक है, constantly the direction of the velocity is changing, so you have to have some centripetal acceleration. ठीक है, but tangential acceleration is not worried about direction, it is worried about magnitude. Magnitude, there is a possibility that there is no change in the magnitude of the velocity, hence a tangential can be zero. If a tangential is zero, if the particle reaches at point B, its velocity will be vb, which is equal to va. The magnitude will remain the same, magnitude will not change in this case. ठीक है, so this creates two types of circular motions. ठीक है, if it reaches C point, again you can say that vc is equals to vb is equals to va, so you can just replace it with v. ठीक है, so all the points are having the same velocity v. ठीक है, this tangential acceleration creates two types of circular motion. ठीक है, it creates two types of circular motion. Types you can write now, types of circular motion. It creates two types of circular motion. One is, first is you can write uniform circular motion. Uniform circular motion. What is uniform circular motion? Nothing, simple. A tangential is zero in this case. Okay, A tangential is zero, then it is a uniform that at any point, if you calculate the velocity, at any point the magnitude of the velocity will be same irrespective of the position and direction of the motion. The magnitude of the velocity will be same. Magnitude of velocity, you can write the velocity's magnitude is constant in uniform circular motion. Okay, but still there is centripetal acceleration in uniform circular motion also. Okay, there will be a centripetal acceleration like this, like this, like this, like this. Why? Because the direction is still changing. Okay, since the direction is still changing, always remember uniform, any kind of circular motion, okay, whether it be uniform or non-uniform, they are always accelerated motions. Okay, you can just write a note here that all circular motions are accelerated motions. Okay, why accelerated motions? Because there is some kind of acceleration always present. Okay, whether your velocity, magnitude of velocity is changing or not, your direction is always changing, hence there is always an acceleration to the system, hence it is always a accelerated motion. You have to remember this can come as a statement. Okay, this can be asked as a statement to you, whether means it they will give you like which of the following statements is correct. Okay, and one of the options will be written that the circular motion, a uniform circular motion, is a non-accelerated motion. Okay, for one moment you will be like, your velocity is not changing, magnitude is not changing, so it should be a non-accelerated motion. Simple. Okay, but wrong. Okay, you have to think about centripetal acceleration also. You were only thinking about tangential, so it became wrong. Okay, all circular motions, whether it be uniform, whether it be non-uniform, they are always accelerated motions. Okay, so this is a very important point you have to remember. Many students I've seen making mistakes in this single point only. Okay, this one point. NEET has also asked many times. Okay, and they like to ask trick questions, so that you can get confused in basic points. So this is a very important thing. Okay, that all circular motions, uniform, non-uniform, are accelerated motions. Okay, acha. Now, one thing you can write in uniform circular motion is that, acha, since A tangential is zero, okay, what can we tell about net acceleration? Okay, the net acceleration at any given point, can be written as a centripetal only. Okay, simple. And the net acceleration in uniform circular motion becomes a centripetal. Okay, because it is a centripetal, because a tangential is 0 in uniform circular motion. Simple. Okay. Acha. But another thing I can say, that a centripetal is always perpendicular to velocity. You can see here. Okay, it is always perpendicular. It is always perpendicular because velocity is along the tangent, but centripetal is along the radius. So radius and tangent, they are always at 90 degrees to each other. Okay, so if a centripetal is perpendicular to the direction of velocity, I can say that the net acceleration is perpendicular to velocity in uniform circular motion. Okay, we are talking just about uniform circular motion. Hence, what I can conclude is that acceleration dot velocity a dot v will be equal to 0 for uniform circular motion. Okay, if two vectors are at 90 degree and you take the dot product, okay, their dot product comes out to be 0. Okay, you know this from vectors. This is basics. Okay, so in many cases, okay, if they want to make a trick question, they will say which of the following is true in circular motion. Okay, in uniform circular motion, they will give you a dot v equal to 0, a cross v is equal to 0. Okay, and both of these, none of these, something like that. Okay, so you just have to remember, in uniform circular motion, net acceleration is perpendicular to velocity because only centripetal is there. If you take the dot product, it will be 0. That's it. Finish. Khatan. Okay, is it clear? Any doubts, anybody? Because these are basic things. Okay, they try to trick you over here. ठीक है. Anybody, any doubt till now? Okay, whatever we have done. Okay, any doubts about this tangential acceleration, centripetal acceleration, and anything about these notes? ठीक है, और यूनिफॉर्म सर्कुलर मोशन. ठीक है. अच्छा. So this was uniform circular motion. ठीक है. Next is your non-uniform circular motion. Non-uniform circular motion. Okay, so in non-uniform circular motion, what is happening, what happens is basically that your A tangential is not equal to 0 this time. Okay, whenever A tangential is not equal to 0, it can be anything. It can be variable, it can be a non-zero constant, it can be positive, it can be negative. Okay, but it should not be 0. That's the important thing. If it is 0, just mute your mics. Okay, somebody's mic is unmuted. Just mute your mic. So what was that? If your A tangential is 0, it is uniform circular motion. If your A tangential is not 0, it is non-uniform circular motion. Simple. Okay. Now there are two cases, okay, which we have already discussed, that there might be two possibilities, that either its velocity will be increasing, okay, velocity like this, A tangential like this, sorry, A tangential like this, A centripetal like this. So its velocity will be increasing in this case. Okay, we have already discussed this, that if it is in the same direction as velocity, the magnitude of speed will be increasing, magnitude of velocity will be increasing. And in the second case, what was happening is that velocity was like this, but A tangential was in this direction and A centripetal was like this. Okay, so these are the two cases in non-uniform circular motion. In one case, the velocity is increasing. in another case the velocity is decreasing. Okay. Now what we can see here is that there are two kinds of acceleration for particle at the same point. Okay, there it is at a point only, but it is having two different acceleration. One is tangential, one is centripetal. Okay, so if I just draw a point outside, this is a point. Okay, I have a acceleration a tangential like this, and I have a acceleration a centripetal like this. Now, if someone asks you, what is the net acceleration in this case? Batao bhai, what should be the net acceleration in this case? Simple. Two vectors at 90 degree, their resultant will be under root of a centripetal square plus a tangential square. Simple. Okay. Result. That's it. Okay, two vectors at 90 degree. That's it. You are able to see only two vectors at 90 degrees. If two vectors are at 90 degree, their resultant is under root of AC square plus AT square. Hence, the net acceleration will be somewhere like this. A net. Okay, something like this. So if I want to draw it in the circle, okay, the net acceleration at this point I will draw it like this. A tangential. Sorry, A net. Not tangential. A net acceleration. Okay. Similarly, for the second type, you can say second variation, I can say that in this case, if I draw for a point, the tangential acceleration is this time downwards and centripetal acceleration is still like this. And still the angle between a centripetal and a tangential is 90 degree. But still you can say that a net will be under root of a centripetal square plus a tangential square only, no doubt in that. So for non-uniform, you can say that net acceleration is having this formula. Okay, for non-uniform circular motion, net acceleration is this. Okay, but the net acceleration's direction will be like this, a net, like this. So if I draw it in the circle, okay, it would be better to understand that net acceleration will be like this. What is the difference? What is the difference? Difference is the angle made by the net velocity and made by the net acceleration and velocity. Okay. If you see in the first case where the velocity was increasing, you can see that the angle between velocity and net acceleration, which is theta, here is acute. Theta is acute. Okay, theta in the first case is acute, and angle between velocity and net acceleration in the second case, that is this. In this case here, theta is obtuse. Theta is obtuse. Okay. So what we can say is that if someone writes a net dot v vector, a net dot v vector. Okay, you know the formula for a net dot v vector. A dot v is av cos theta. Av cos theta. A is the magnitude, v is the magnitude. So they will be positive. But cos theta, if theta is acute, cos theta will be positive. Okay, just try to visualize this in your brain. Okay, in your mind. Okay, it will simplify things in physics. Okay, av cos theta I'm saying. AV cos theta, basic formula of dot product. A is positive, V is positive. Cos theta is the term which is varying over here. Okay, it can be positive, it can be negative. Since theta is acute, okay, like it can be 30 degree, 60 degree, and a 45 degree. So all these, if you write cos 60, cos 30, cos 45, all are positive values only. They are never negative. Okay, so A dot V in this case will come out to be positive. Okay, or you can write it like this, that A dot V is greater than 0. Screen is stuck. Just wait 3 minutes to get, because the network is completely fine. ठीक है, just wait 2-3 minutes. It should clear out. Acha. What was I saying? That in first case where the angle between acceleration and velocity is acute, the dot product of net acceleration with velocity will be positive. Okay, I'm not writing anything, you just have to visualize it in your minds. Okay, try to visualize it. है ना? हाँ, magnitude will be this only. Magnitude is always calculated by under root of a centripetal plus a tangential square. Okay, that is not an issue. But the direction is the difference. Okay, only the difference between these two cases is the direction of net acceleration. In one case, the direction is making an acute angle with velocity. In other case, it is making an obtuse angle with velocity. Okay. Acha. And for the second case, what we can say is that if theta is obtuse, how will it be acute? See what I've done here. See, just try to see in the circular motion only. See, my velocity is like this. Okay, velocity is in this direction. A tangential is like this, and a centripetal is like this. These are the two components which are creating your net acceleration. Simple. Okay, two components which are creating net acceleration. So if you take the resultant of a tangential and a centripetal, okay, definitely the net acceleration will be in this direction only. And just by seeing at the geometry, just by looking at the geometry, you can say that it will be making an acute angle with the velocity. Simple. Okay. Yes. I guess you're getting it, because see, I am saying acute just by geometry. Okay, you can also understand it. See that if a centripetal is like this, a tangential is like this, then if a net is like this, the angle between these two will be theta only. This is y direction and this is minus x direction. So angle with the y direction is what? It is theta, and that will be acute. Okay. Now just imagine you start to reduce the a tangential. Okay, you start reducing the value of a tangential. A tangential now becomes smaller like this. Okay, so you can see that the net acceleration will be somewhat like this. The angle has increased. From the previous case, the angle has increased. Suppose your a tangential now becomes like this, then the net acceleration will come out in this direction. So with the positive y direction, the angle is becoming how much? It is becoming obtuse. Okay, so my velocity, see, you can see in both the cases, my velocity is in positive y only. Okay, but as the direction of tangential acceleration is changing, my direction of net acceleration is changing, thus creating a change in angle with the positive y direction. Okay, is it understandable, or should I explain it more? Okay, I guess it is clear. Yeah, that's it. Okay, so this is the basic. Okay, you should know this. Okay, no problem. You are having problems in this. Okay, it creates confusion. Okay, there should be problem. If you are not getting problem, it is very good. But if you are getting problem, just clear it now. Okay, because these are basics. This will be used everywhere. Okay, in all of the chapters it will be used. You know this. Acha. Because they want to represent a dot v. Okay, they are trying to calculate a dot v. Okay, it is basically a previous year question, okay, of NEET, that what is the value of a dot v for a uniformly accelerating circular motion. Okay, uniformly retarding circular motion, they have asked previously such questions, so that is why we are including it in theory. Okay, that is why with v only we are taking. Okay, you can take it with radius vector also, you can take it with centripetal acceleration also, you can take it with any vector which you like. Okay, but with velocity, velocity is kind of a reference point. ठीक है, it is kind of a reference vector. So that is why with respect to the reference vector we are taking the dot product. So that is why we need the angle with velocity. ठीक है, you can calculate a dot r vector, no problem. ठीक है, a net dot r will be greater than 0 in this case. Simple, because again you see what is r vector, radius vector r vector is like this. Again the angle between r vector and a vector, sorry, it will be negative, it will be negative. ठीक है, r vector and a vector, you can see that r vector will go like this. So the angle between r vector and a vector here is obtuse. ठीक है, if it is obtuse, so again it will be negative. So you can vary things. ठीक है, you can create variations, but the reference is velocity. ठीक है, our reference is velocity, so you don't have to worry about radius vector and all. ठीक है, if it comes, you can think about it. You just have to look for the angle. ठीक है, you just have to look for the angle. ठीक है, because this is creating the idea in your mind. ठीक है, that if I know the angle, I can predict whether the dot product will be positive or negative. Simple. If it is acute, dot product is positive. If it is obtuse, dot product is negative. Simple. Okay, so that is what we will write here, that a net dot v in the second case will be negative because cos of obtuse angle is negative. So a dot v comes out to be less than 0. Okay, is it clear? And if you want with respect to r, we can discuss that also. Okay, but it won't be useful. Okay, they don't try to talk about it, but still, if you want it, we can discuss it. Okay, let's just discuss this. We have 3 minutes left. Okay, questions, most probably try to do it yourself. Okay, or if you want, I will talk to sir. He will do some examples in the next class. Okay, no problem. And acha, before that, with r vector. Okay, with r vector, let's see. In the first case, in the left hand side case where the velocity was increasing, you can draw the r vector like this. This is the r vector, this is the velocity vector, and this is the a net vector. Okay, you have drawn these three things. Okay, now you need what? You need the angle between vectors. Okay, for that the tails of all the vectors should be coinciding. Okay, so what I do is I move this r vector forward like this. Okay, so that the tails of r vector, v vector, and a net vector are at the same point. Okay, if now you can calculate any dot product. Okay, if you want v dot r 90 degree, 0, v dot r is 0. You want a dot v, okay, a dot v, theta is acute. Okay, between a and v, theta is acute, positive. Okay, you want a dot r. Okay, you want a dot r, angle here between a and r is what? It is obtuse, negative. Khatam. You can do anything. Okay, any combination you can create over here once you know the vectors. Okay, for the second case, let's see. For this one, if I am talking about, this is your r vector, this is your v vector, and this is your a net vector. So again, the same problem. Okay, you need to create, it means you need to coincide the tails of all the vectors. So what I will do, I will move r vector forward like this. Okay, again, v and r are at 90 degree. So v dot r will be 0. Again, no problem. Okay, again, a dot v, a dot v, a dot v is obtuse here. Okay, you can see it is obtuse angle. So if it is obtuse, it will be negative. It will be negative. A dot r, a dot r, just see the angle between a and r is again obtuse. It is again obtuse. So it is again negative. Okay. So once you have the directions, once you have the angles between the vectors, you can easily predict the dot products. Okay, just the direction, just the sign we need. Okay, whether it will be positive or negative. And no one is going to ask you the magnitude, but positive, negative is important. Okay, so this is your circular motion. Okay, is that clear? And so ठीक है, we could not get time to calculate questions. ठीक है, do questions. ठीक है, I will just talk to sir. ठीक है, and tell him that questions were left to discuss. ठीक है, I have done the theory and all. ठीक है, try to do questions yourself. ठीक है, because once you know the basics, once you know the theory, try to do questions yourself. You will have more understanding. ठीक है, so that's it for today. Thank you. Thank you.